Welcome back again to Balvikyan Bharti with Vilas Sarkar. Now we will move on to the definition of viscosity and their mathematical relations establishment. Okay, so I will derive the mathematical relation of viscosity. So, as I given an example that if a fluid is flowing between the two solid layers, parallelly placed solid layers, one is at rest, another is moving. Okay, so as we already discussed that the layer which is adjacent to that are getting higher velocity, similarly it will slow down towards the rest. So of that few, if I take two of the streamline which is at a distance of y and delta y plus delta y, this, let's say at y that velocity is v of this streamline, and at y plus delta y it is at velocity of delta delta v. Okay, so now this is having a marginally difference between these two layers. We are talking about very infinitesimal small distance delta y and the deviation. Okay, fine. So if I take that in picture, so if I can consider an element of this shape in between two streamline. So this streamline, I am just taking this as a element between this part. Okay, so now if I draw it here with an enlarged view, so this is basically what is happening. This layer moving fast at any point of time t, this edges this point and this point is at vertically in the same line. After time t, this may be moving faster, so this is at delta x axial movement, and this also delta x axial movement, and this is causing a deflection of delta phi, and this is at point t plus delta t time. They are very finitesimal small distances we are talking about. So this, if it is y, this also delta y is also considered to be delta y. This is not much deviation because this is very small, tiny. So this this triangle is almost a arc, or as because it is small, we can take it as a just a triangle. So this, if it is theta, this is r, this is s, arc length. So this can be a thing we can consider for a very finitesimal small segment. S is equal to r theta, that is being used for arc, for a circular path. So if that path is very small, so this also we can take the error, instead of an arc, this is a straight line, and we can eliminate that error in our consideration. Okay, so S is equal to r theta, and S is what, that this is delta x, and what is r here, delta y, and theta is equal to delta phi you have taken, so delta phi. Okay, we'll take it delta phi. So what is your means delta phi is equal to delta x. So why you are talking about delta phi? So this is the deflection of angle. Okay, so any deflection in angle, is the deflection will affect in the surface. So if I talk about the strain is nothing but your delta phi, the angular strain. So that means strain is nothing but the ratio of same what we can say between same linear dimension. Okay, so strain is nothing but the deflection of two linear dimension. Okay, strain is deflection of two linear, because with respect to this is at this point, with respect to this now it is this point. So your with respect to this dimension, this is deflection is this much. So this is the angular deflection or the angular strain it is produced, and strain is nothing but any uneven forces between two layers will cause it to move some distance, but if it is elastic it will try to move back, so that will cause it a temporary deflection between these two. If I can consider about some body which is very flexible, let's say we are talking about rubber. Now if I give a force on the top surface of the rubber may be deflected like that. Okay, but if I release that force, it will come back to this position. So this is the case, this is the strain produced on the rubber between the top and the bottom layer due to this extra force. So strain is a deflection of from its original position to a new position. So this is the strain deflection. Now this can be said to be between two linear dimension. The delta x deflected against the distance between the 2 points from the initial position. This is the referral point. With that respect, at point T, this is on the same vertical line, but it is deflected. So this is the deflection of x with respect to the distance between the layers. So this is called the strain. Okay. Now we have understood strain. Now what else is viscosity? So viscosity is, by definition, viscosity or the basically the dynamic viscosity is the stress upon strain rate. Strain rate. So what is stress? Stress is force per area. Okay. Now if it stress is force per area, then what is the force here? The force that this layer is being resisted by the bottom layer on the opposite direction. As I said, this is getting a force that is Fv, that is viscous force or the frictional resistance. So the force, viscous force is Fv or the frictional resistance upon, if I say this is causing a cross section of this solid path, if it is this way, so the liquid in between interrupt will get the same force this area. So this is the area, the force is applied on the whole area of the surface it is contacted with the solid surface. The force by area, this is your stress, and strain already we have getting, it is delta phi. So if I put it like that, Fv by A, sorry, if V by A on the top with this stress, and strain rate is already taken, delta phi rate means delta by delta T. Why? Because this deflection, what I have shown earlier, this deflection is causing in time T to T plus delta T. So this is causing in delta T. So this is the rate of deflection in time delta T. So if I say, this can be written as Fv upon A divided by delta phi, whatever I have got. This is delta x, delta y. So delta phi, we have arrived at this one. So you can write delta x by delta y into delta t. What is this? This is your delta x by delta t. Can it be written as delta v, the velocity along this direction? Okay. So this is Fv by A upon delta v by delta y. So this is what? This is your velocity gradient. This is your velocity gradient at any time. Okay, so this is called your dynamic viscosity as per the definition. So if it is so, so it can be simplified. F by V by A is equal to eta delta V by delta Y, and now this can be written as equal to A will be there, but this need have some sign means consideration. Why? Because FV is acting on opposite side, whereas velocity is moving in this way. The fluid is moving in this direction. Velocity is vector. FV is a force, that also is a vector. Now force is a vector, velocity. If we take this as a positive direction, so this must have a opposite direction to velocity. So if I say this is, so this will be the correct formula for the viscosity force or the frictional force is will come with a negative sign with this. Okay. Fine. So now we can see one more thing, that is, in the initial case, in the last lecture, what I have shown you, these are the two solid surfaces. One is at rest, another is moving. What I have shown you, this is the distance y. Now if I move this way, at rest your Fv is maximum, so this will be the maximum, so your velocity is minimum here, the velocity is 0, and the velocity curve was like that only, I said, and your resistance curve is this way, so resistance maximum this way. Now see, Fp is inversely proportional to your y. So more you, although it is delta y, but it is ultimately the distance now. Delta y is this way, delta y, the measurement is this way. So y is moving from this way. So more the y, lesser is the Fv. You can see, and this is coming with the negative sign. So that means the direction of Fv is opposite direction, and it is inversely proportionate but linearly related. Inversely proportionate, linear, but the order is both are having 1. So as you move y, the Fv will reduce, and with V, if I say, it is directly proportionate. So that means now with V, if it is increasing this way, that means from, if I consider these 2 points with regards to these 2 points, that V here, it is delta V is positive. So if delta V is positive and delta Y also positive, if I move up, delta Y is positive, so that means V, the Fv with respect to this is negative. The total result is negative. That means with this has to be lesser, otherwise the result will not come negative. So with the velocity moving up, the Fv, the resistance due to the flow is reducing. So this also represented all this criteria. So the graph will be from zero, the maximum, that velocity will get the maximum velocity here, and from 0, this shearing force is 0, it will attain the maximum shearing force here, or the resistance of, or the Fv, whatever you say. I am talking about tau. Tau is nothing but the Fv by A. This is the shearing force. Okay, this is represented by tau, the shearing force. Okay, this is by the viscous resistance or the resistance, frictional resistance upon the area. This is also the same term. So tau will be the 0 here to the maximum here, velocity will be the 0 here, and we will get the maximum. So this can be represented, can be explained with this formula. So this is the viscosity. Okay, now to establish some more relations will, as we have said, that velocity with the direction means from the distance with the reference frame towards the moving plane, it is parabolic nature. So to understand that, we have to means derive one relation. So that relation we'll do it right now. So this is a cylindrical path through which the fluid is flowing. Okay, this is the central line. Okay, let's say I am taking some element here, okay. So if I elaborate this, okay, if I take the enlarged view so that I can explain the thing better way. So as because this is matching the center line, for the symmetry I am taking at the center, whereas you can take at any point, but for the symmetry I am saying this. So this is, let's say, the maximum radius is r, and this is, you can say, twice r, that means dh, hydraulic diameter, you can say. Whereas for this I am taking, this is L, the length of the element, this I am taking as r, the radius of the element, okay. And few more things, this is flowing this way, velocity is this way. So definitely there is a pressure on the both side, there is a difference in pressure both side, and this P1 must be more than P2. Okay, now what else? As it is flowing, this element, if I talk about this element separately, this could be assumed to be a solid cylinder having surface area of with accordingly to the r, and it is getting a this frictional force around this surface. So this is a circular surface, okay, this is a circular surface, and on its perimeter or periphery it is getting that frictional force. So as we said, that we are talking about the Newtonian fluid. So in Newtonian fluid, the thing that we have we are assuming, that is the convective, that term already have acceleration is equal to 0. That I have already talked about this, but I didn't explain it. So what is that? The convective is that when the layer is moving one after one, this layer is giving a frictional force this way. Okay. Now this is getting a force this way due to the solid layer, if it is in just added to the solid surface. But this, as is getting a momentum due to the solid surface as it is moving, and this is, let's say, static, v is equal to 0. This is moving, this is giving a momentum to this surface, this is giving resistance, but the layer which is adjacent to the solid is getting a momentum, and this momentum is being transferred to this layer. So this is getting a force this direction, the next layer is giving a force this direction. So there is a resultant force due to that. This, if I consider this resultant force F net is equal to m into ax. Ax is the acceleration along the x direction for this layer, this streamline I am talking about. So as because this is Newtonian fluid, this will follow the second law of Newton. So this will follow the second law of Newton. The second law of Newton is force is equal to mass into acceleration. That will definitely follow. So when the layer is following this way, this layer is dragging this next layer due to the resultant force towards the same direction it is moving. But the force effectiveness is less and it is getting lesser velocity. But thing is that as because there is a force balance, that definitely you will get an acceleration. But the consideration that when we are talking about the laminar flow with the Newtonian fluid, this acceleration AX, that convective acceleration, this is called the convective acceleration, where the layer is getting accelerated due to the next layer which is dragging it, getting an acceleration. But this acceleration for this kind of fluid flow description or analysis will take this convective acceleration is 0. Okay, this is my another basis or the acceptance for this flow analysis. Okay, so that convective acceleration is 0. Okay, so that means there is no net force. If it is 0, so there is no net force acting between the layer upon layer. So the whatever the velocity, whatever the force is, it is uniformly maintaining the velocity. There is no acceleration is maintained. As acceleration is 0, so that means that change in velocity upon change in time along this axis is equal to 0. So that means Vx is constant. Okay, the velocity along the x-axis is constant. So this is the one assumption or the acceptance for this kind of flow. This has to be, what are those? Laminar flow, Newtonian fluid. Third one is convective acceleration is 0. That means the velocity is constant along flow direction. So these are the assumptions. Okay, now if it is the case, so if net has to be 0. So for this case, if I derive the free body diagram, this is the free body diagram where the forces are, this is pressure force, okay, and there is a the frictional force on the circumference. So what are the force? P1 minus P2, that is acting on the area, this minus, why minus? If this is the direction of pressure force, due to that the flow is established, if I take it is positive, the other, that frictional force in the opposite direction, this has to be in the opposite direction. The frictional force is shearing stress, and that is acting on 2 pi r into L. 2 pi r, that means the surrounding of this, into the length, the total surface area, that into the shearing stress that is acting on the area. So per area force, that is the complete force, and the net force has to be 0. Okay, so if it is so, you can get this P minus P2, P1 minus P2, that is the differential pressure between these two surface. If I take, this is 0.1, this is 0.2, this is P1 minus P2 is delta P. So you can replace it with delta P into area, that means the circular area, pi r square minus tau, the shearing stress, into 2 pi r L is equal to 0. And pi r can be cancelled out because this cannot be 0. So delta P into r will be there, minus tau into 2L will be there, is equal to 0. So our case tau, the shearing stress, is equal to delta P into r divided by 2L. That will be the relation for shearing stress. Okay, now again the shearing stress, as I said, is Fv by A, isn't it? So that is equal to minus Fb is equal to, by A, we can do eta A into that, we can take delta V by delta Y, or here as it is circular, Y could be the, can be R, so you can take it as R. Okay, now this is eta, both we can equalize. So this is equal to delta P into r by 2l. Okay, now we'll move with this equation. So if I move with this equation, so what are the variables? dv, if I take it one side, it will be the other side, minus will be there, delta p will be there, divided by 2al will be there, 2al no, a will not be there because f by a already have taken as a ta, so a will not be there, sorry, this will be not there because fv by a is tau na, so that is equal to this much only, so a will not be there. Okay, fine, so a will not be there, 2l minus is there, eta will be there with this eta, and the remaining is r into delta r, dv r into delta dp 2 neta by l is there. Okay, fine. So these are the final form of the equation. Now delta r, if it is finitesimal small, it is very small, so in that case this can be considered as dr, and accordingly delta v can be considered as dv. Now if I move like that, so this equation can be represented as dv equal to minus delta p or dp, you can say. This is almost pressure difference dp, or this delta p you can leave it like that. Why I am saying, I will explain it. Delta p 2 into eta l into r dr. Now integrate on the both sides. The variables are r and v, because the variation only happening with respect to r and v, velocity. Delta p, if this conduit is fixed, so the pressure whatever is acting, if I consider the whole duct as a whole, the pressure here and here, only the case that has to be considered, because elementally we will not consider the pressure every point, we will consider the pressure for which the flow is happening. So this delta p is nothing but the extreme pressure, so that we can consider. Okay, so this may be a constant delta p. For the sake of the calculation, I have taken this element, that's why I have taken d, but delta p you can take as a whole. But this variation, even though if I take the whole delta p, it will be the similar way as it is moving for this case also, for element also. So this is minus will come 2 eta l, and if we integrate that, that will become v, and this will become r square by 2 r dr r square by 2 plus one constant will come. Okay, now this is the empirical formula, and this is depending on r, with only variable is r, more r is varying with this. Now constant having some value that may be calculated, but you can see r having 2 order and v is having 1 order. So but why I am saying, because more you move r up, r is r, if it is increasing from r can be started from 0. If you put 0, vr will be the c constant only. If you, so this is basically vr into some, let's say some constant I am talking, this part I am talking as some constant into this with 2 also. So I am giving it a this by r square. So this is of this form. Okay, now if I increase r from 0, it is having c value. If I increase r, so this part is positive, this cannot be negative. So something is a constant minus something, it will reduce the value. So more you go up, your velocity from the, this having the maximum velocity. Okay, if I consider this is in the maximum velocity. So what is this? This is static part. In other case, what I have shown, this is at rest, this is moving. So the velocity is moving like that. So more you move toward the moving part, the velocity is higher. So more we moving to the moving part. This is under less resistance. So this is the static one. Static is the velocity 0. This is velocity 0. More you moving to the moving part. This can be taken as a sliding surface while having less resistance. At the center of the tube, there is less resistance. More you move to the static part, it will get more resistance. So velocity curve will be the same on the both side. So but if we consider the half of this, the velocity is like that. That's similar to that, and that is because this parabolic relation. Understand that depends on the square of the resistance. So more move, that will be parallel, not a linear. Okay, so that's why I just derived this formula to understand why that velocity for case of laminar flow, it depends with the distance it is moving from the rest towards the moving part, because so this is related. Now if I consider this want to calculate the C value, what is C value, how will you get that? The C will be when R is equal to 0, that when R is equal to this is velocity, here it is 0. So this velocity at R, the maximum is R is equal to capital R, your velocity is 0, you can put this there. So 0 is equal to C minus K into R square. The K has some value, so that C value is K into R square. Okay, now I put this value here. If I replace the C, it is nothing but K into capital R square minus A into small r square. So now VR is equal to K into, if I take R square capital 1 minus R square by R square. This is the case. Now K into R square, I'll give it another constant name. This is, so what is this value exactly? So K we have taken this one. Now we plug with R square. So this is K1 is equal to delta P for eta L into R square. Okay, so this is R. R can be represented as with a hydraulic diameter. R is nothing but dH by 2 hydraulic diameter, because this is known figure in viscosity formula that was there. So I will not talk about the small capital R. Instead that we will put the value of eta L into R means dH square by 4. So that ultimately delta P into dH square divided by 16 eta into L. So this value is called the critical velocity. This is constant. So for any pipeline when the fluid is flowing, this Vc is constant and Vc is called the critical velocity. So in formula we can write the variation of the fluid is critical velocity is 1 minus small r square by capital R square, or if it is hydraulic diameter is 2r by capital DH whole square. You can put it in another bracket. This will be your variation of velocity with respect to R. This will be formulated like that. So this DH is the hydraulic diameter, and that R is the diameter of any streamline or any layer from the center line. Understand? So this is the derivation. This is being used to understand why that variation of V is like that. Is a parabolic one. Okay. So I will stop it here. In the next video, I will start from the Stokes law. Okay. So that is the last part of this lecture, and then after we will do some mathematics or solution problem solving session. Okay. So thank you for now.